Go ahead.
Thanks very much, David. Let me just put the full screen on. So let me start by apologizing for the technical issues that I had yesterday, and thank the organisers for finding another time that I could give my talk today. So thanks very much for that. This is a joint work with Jerome Barkin and Ganesh. Jerome's work on this project was supported by a Macquarie undergraduate research internship. He worked on this project a couple of years back. He's at Reserve Bank of Australia now. This isn't going to be a very technical talk, but there are a few references and things. I've put a copy of the slides at this web page, so if anyone wants to download that, they can pick up some details if they missed them. So I'm going to start with some preliminaries. In this talk, I'm interested in scattered fields US that satisfy the 2D Helmholtz equation exterior to some scatterer D, and also US satisfies the Summerfield radiation condition. And then US is induced through interaction of some incident field with the scatterer. And in this talk, I'm going to assume that we've got a sound soft boundary condition on the boundary of the scatterer. And I've highlighted this part that the total field vanishes because I'm going to refer to that in a couple of minutes' time. Of course, if we take a particular limit of the scattered field, then we get the far field that just depends on observation direction. So to motivate the talk, this is a plot of the far field of a particular object. And what I'm going to do, I'm going to use that far field to compute the radiating wave function expansion of the scattered field. So this is the radiating wave function expansion. The HNs there are the Hankel functions. The ANs are the coefficients. And I'm not going to say much about them now, but I'm going to explain how we can compute those ANs from the far field in a couple of minutes' time. But the key point for now is that once I've got the scattered field, I can add on the incident field to get the total field. And this is a plot of the absolute value of the total field. And now I remind you that on the boundary of the obstacle, the total field vanishes. So we can look in this figure for where the total field vanishes, and it should reveal to us the shape of the object. Now, personally, I don't find it very easy to see the shape of the object in this figure. I find it easier to plot what I call the indicator function. So 1 over the absolute value of U, and I've used a log color scheme here. And what we see is that where the indicator function blows up, this red color reveals the shape of the boundary. And we can see that the scatterer was this ellipse shape. Now, I'm going to just jump back to the previous figure. And what we see is that close to the origin, there's something strange going on. Actually, what's happened is that the scattered field is blown up close to the origin. And so although the motivation for this talk is the inverse problem, really what this talk is about is what's going on in this region close to the origin and some analysis about what's going on in this region close to the origin. So before I get into a bit more detail, I just want to make some preliminary comments. One is that, of course, in practice, we need to truncate that wave function expansion for the scattered field. And so I'm going to do that with truncation parameter big N. And then, of course, if we don't take big N big enough, then we don't get convergence to the true scattered field. On the other hand, and this is a kind of common issue with inverse problems, if we take N too big, then we will amplify any noise in our far field and we won't get a very sensible result. And just to demonstrate where that noise comes from, this is a plot of the first few Hankel functions. And if I pick a T, then maybe here's better. You can see that as N increases, the size of these Hankel functions gets bigger and they actually blow up as N goes to infinity. And that's where this amplification comes from. Okay, so I said earlier that we can get those AN coefficients from the far field. We've got a two-step method to compute those coefficients. The first step is very simple. We actually just compute the Fourier transform of the far field to get these UN hat infinity coefficients. And then the second step is we just scale them. And the scaling factor, so there's Hn in the scaling factor, as you can think of that as the far field of the Hankel functions. Now, I've called that coefficient there An tilde because it's actually an approximation to the true An. Why is it an approximation? It's because up in step 1, we actually used a discrete approximation to the standard inner product using a quadrature rule. So there are 3 applications of this 2-step method. The first one is you can use it to compute the T matrix. It's actually a very good way to compute the T matrix because it's much more numerically stable than the standard methods to compute the T matrix, like the null field method. And I talked about using this 2-step method to compute the T matrix in KOZWaves 2015 in Adelaide. Another application is to compute the interactions between scatterers in large-scale multiple scattering simulations. I talked about that. It was in a different life. It was my last trip anywhere in this time in 2020 in Melbourne. And then the third application is this inverse problem application, which is what I'm talking about today. And the references there cover those 3 applications. So, okay, I'm gonna give a bit of analysis next. I don't like to give technical talks. I'm really just going to try and give a flavor of the main results. I already said that there are 2 issues that we need to consider. The first one is convergence of the radiating wave function expansion, and the second one is stability. And the questions that I'm interested to answer are, so the first one, we've already seen that something strange happens close to the origin. So the big question is, we can kind of see the scattered field with our method. How close to the origin can we see with this method before these strange things happen? Then in doing that, what is the best choice of the truncation parameter to minimize the error in our reconstructed scattered field? And then when we choose the best N, how accurate actually is our reconstructed scattered field? So these are the 3 questions that I'm going to address with the analysis. So let's look at the convergence part first. What I'm going to do first of all is I'm going to define U-rad to be the wave function expansion. Actually, this is the same wave function expansion as before. I'm just being a bit careful with my notation because the scattered field US is actually only defined in the exterior of the scatterer, whereas this U-rad, I can evaluate that anywhere apart from the origin, provided this series converges. So I'm just going to be a bit careful about my notation there. And then what I'm going to do is I'm going to introduce this L2 type sequence space HR dash, and a sequence AN is in HR dash if it satisfies this decay condition. And it's useful to introduce these kind of sequence spaces because it's easy to show that the sequence AN is in HR dash if and only if the corresponding U-rad restricted to the sphere of radius R dash is in L2. So we've got this equivalence between nice behavior of the radiating field and belonging in this sequence space. Now there's actually a convergence result that's interesting here due to Kirsch, which says that the sequence AN is in HR dash for all R dash bigger than R, where R is the radius of the circumscribing circle of the scatterer. But in this figure up here, I've plotted, so the blue crosses are the absolute values of the ANs for a scatterer with radius 1.2, with the circumscribing circle has got radius 1.2. But you can see here that these coefficients actually sit in H about 0.6. So we've got a much stronger result holds for the scatterer than is given by the convergence result by Kirsch. In fact, it looks like numerical evidence suggests that we can replace R with R0 for some R0 less than R. And at the moment, I'm not going to say what this R0 is, but it looks like a much stronger result holds for the convergence of this sequence. Okay, now let's look at stability. So that really this is about if we've got any noise in our far field, and how does that get amplified into the near field? And to answer that question, what I'm going to do, I'm going to define this Wn rad is a radiating wave function expansion. And then Wn infinity is the corresponding far field of that radiating wave function expansion. You see they've got the same coefficients there. And it's not too hard to prove that the value of this W rad in the near field is bounded in terms of the norm of its far field, but multiplied by this thing highlighted in yellow is this amplification factor. And it's basically what you get if you put the Hankel functions in a vector and take the two norm, you get this amplification factor. But it's dominated, of course, by the big N order Hankel function. So what I can do is I can combine those two what would you say, strands of thinking into our main result. And the setting for this main result is if we've got noisy data, noisy far field data V that approximates the true far field U. So I think on the previous slide, think W is U minus V. Then we can bound the error in our truncated wave function expansion in terms of these two terms. The first term is basically just convergence of the truncated expansion. So the blue one is just basically about convergence. And then this pink term is a bit more interesting. So I ran out of space. I've got this M term. M is down here. The first two terms, I'm not going to say much about them, but they actually come from the quadrature rule that we use to compute the coefficient. So they're basically about the accuracy of the quadrature rule. And if V and U, the far fields, are smooth, then these two terms decay extremely quickly with respect to N. So these terms are really very, very small. Most times we can neglect them, and then the third term becomes important. So what I'm going to do, I'm just going to put an approximate bound up here with the third term. And what this pink term now says is that we've got the error in the far field, but multiplied by this Hankel function amplification factor. So now I'm going to show you what that looks like. So these are results for scattering by an ellipse. And let's look at the left picture first. This is N on the bottom and the error on the left, on the y-axis. And the blue lines are actually the blue bound evaluated for different R's, for X with a different distance from the origin. And you see, of course, you'd expect that these have got negative slope. Their error goes down as N increases. And the pink lines actually come from that pink bound, the second bound, and these show the amplification by the Hankel functions. And the solid black lines are numerical results. So the first thing to say is that we get an extremely good agreement between our bounds and between our numerical results. But the main thing that I want to point out is that for any given radius, we can find the intersection of the blue line and the pink line, and that gives us our optimal N, our optimal choice of truncation parameter to reduce the error. And then we can just read off the error from the y-axis. So we've got this useful kind of following on from our bound. We can choose our optimum N. The V infinity for this left figure was obtained from U infinity with random noise with standard deviation sigma. If I reduce the standard deviation of the noise, then what happens is that those pink lines move down and to the right, and so we get something like this, and that reduces the error in our reconstruction.
Sorry, Stuart, that's 14 minutes.
Okay, great. So I've got some results for a couple of more shapes that I don't really need to talk about. They're very, very similar. But what I want to show you next is a plot of the indicator function. So on this plot, I've marked in the ball of radius R0. And what we see is that inside that ball of radius R0, we don't really get anything. We get this just noise that's caused by the blow up from the Hankel functions. But outside that ball, we get a pretty good reconstruction of the image. And so it seems like this is working quite nicely. If we reduce the noise, then we get an even better reconstruction. This is a similar figure, but for an ellipse with a longer aspect ratio. And I'm showing you this because there's something important and interesting happens. For the ellipse with a longer aspect ratio, the R0, the decay rate of the coefficients, the R0 is actually bigger. And so what we find is that there's this, we can't see as close to the origin. We get this ball where we can't see anything. But outside that ball, we get a remarkably good reconstruction of the scatter. Just very, very quickly, just to convince you that this n that we choose is the right one, the figure in the middle is the optimal n. If I reduce n a little bit, then I lose the reconstruction in this region. That's because the series hasn't converged. If I increase n a little bit, then I lose reconstruction too, because I've blown up the noise in my data too much. So okay, let me jump to the conclusions. What's the best choice of n to minimize the error? Well, we can determine that by the intersection of our blue and pink error bounds. Then we can read off the error that we get and determine how accurately the US can be computed. How close to the origin can we see? Well, we can actually predict that from the decay rate of the ANs. We can get R0 as a lower bound. How close we can see may increase depending on the noise. All right, let me stop there. Thank you.
Thank you very much, Stuart. Are there any questions?